Okay, I'm going to complete Chapter 4 with a discussion about the cycloalkane rings. To start with, cycloalkane rings, in order to make a ring, require that you take a hydrogen off either end of a chain to make a new place where you can make another carbon-carbon bond. And anytime you lose hydrogen, you're doing some kind of an oxidation on the carbon in question. So we have this generic formula for alkanes of CnH2n plus 2, and when you look at the generic formula for a ring, a compound that contains only one ring, with N carbons, the formula is CnH2n plus, reflecting the fact that you lost the other two hydrogens. And so since the maximum number of hydrogens that you can have is the alkane formula, if you've lost some hydrogens, we say that the molecule has been somewhat unsaturated. And that term that we use for that is unsaturation, or for each two hydrogens that you lose, we call that a point of unsaturation. Now in the book they might call it a degree of unsaturation, but I use points of unsaturation so that it's not confusing when we talk about degrees of carbon, and we have a different term for this. So the properties of the cycloalkanes are similar to the properties of hydrocarbons, except that for the branches and the groups attached to the ring, they're also going to interfere with the attractive forces between the molecules, and so that would lower the boiling points. And so they'll be similar for the same number of carbons given that constraint of branchiness. And we're going to assume in this book that the cycloalkanes behave pretty much like the alkanes in that they're fairly inert to reactivity. But in fact, cyclopropanes are a little bit more reactive than other cycloalkanes, and we'll talk a little bit more about that later. So when the idea of making rings of carbon was first discovered, not very much was known about how molecules were put together. And the person who first proposed a way of deciding about the stability of the rings was Alfred von Baeyer. And he's the same person that you might have heard of with Bayer aspirin. It was he that first synthesized aspirin. And the company founded based on his name has since lost the patent for making aspirin, oddly enough. But anyway, he said that the stability of the rings would be related to the angles, and so he compared a series of ring sizes to the geometric shapes. And the strain associated with the bond angles was what he was thinking would be the determining factor. And it is true that it is a factor, but the data suggests that that's not all there is. And because if angle strain was the only thing that mattered, then cyclopentane would be the most stable ring, and it is not. Now remember what angle strain is. It is the energy associated with the deviation of the bond angle from what it ideally would want to be for whatever that hybridization of carbon is. So here's a chart where the combustion data has been collected on a series of rings and divided by the units, however many CH2 units there are in the ring. So a 3-carbon ring has 3 CH2 units, so they get the heat of combustion, and you see that the cyclopropane ring has the highest amount of energy released from combustion of a 3-membered ring per CH2 unit, and it drops off sharply as you go, but you notice that 0 is not at a 5-membered ring, it's at a 6-membered ring. Then it goes back up a bit, and then finally it drops off to 0 at really large ring sizes. So we want to kind of understand this trend, and clearly it's going to have something to do with things other than just angle strain. So we know what angle strain is, And we're going to look some more at that and compare it to the geometric shapes. Some other possible strains are torsional strain, which is anything that interferes with free bond rotation, and so how much the ring carbons can flop around basically. And also the possibility of steric strain exists. And we've just talked about that, where you're looking down a bond and you're trying to decide if there are groups that are kind of getting in each other's way. Remember, steric strain is two things can't occupy the same space at the same time. And so we're going to look down the bonds and look at the dihedral angles, and if it's 0 degrees or it's close to 0 degrees and eclipsing is going on, that would be bad, or that would mean there's a lot of steric strain. And if you have 60 degrees or close to 60 degrees, that's better. There's everybody's got more room, and so that would minimize the steric strain. Now, we're going to look at some pictures of some different rings and different ways of looking at them. And so we have the space filling model here, and we have a ball and stick model, and then we're looking down one of these bonds to look at cyclopropane, and you see that the hydrogens are eclipsing each other. And actually that would be true. All of these hydrogens are eclipsing each other on the top and on the bottom. And so cyclopropane is very strained from that standpoint. And also because it takes 3 points to make a plane, there's absolutely no freedom of motion whatsoever in this molecule. When we go down to cyclobutane, they've shown you here one possible conformer, and if you built this model, you can wiggle it a little bit, but not very much. And so if you just choose a conformer and look down one of these bonds, and so they're showing you're looking down this bond, and so here it is pictured in the Newman projection. You see you're not quite eclipsing, but it's pretty close. And any of these bonds that you look at, you're going to see something similar, that there's a lot of almost eclipsing going on. And there is a little bit of wiggle in this molecule, so the torsional strain is not quite as bad. This is why in construction you'll find that a triangle is a stronger feature to have in a constructed bridge or building than a square, because there is still some freedom for motion to occur for the building to fall down if you don't have any triangles. When we go up to cyclopentane, this is the molecule that Alfred von Baer thought would be the most stable because of the angles. And but if we look at again, choose an A conformer and look down the bonds, you can see, well, that one's not too bad. But if you look around at each one of these bonds, you're going to see that some of them, like this one back here, it looks like they're pretty close to eclipsing each other. This one right here doesn't look too bad. This one doesn't look too bad. This one looks okay, but these two and these two look like they're pretty close, or less than ideal in terms of the dihedral angles for those conformers. And even if you wiggle it and choose another conformer, you're going to see some that are okay, some not so okay in terms of the steric problem. And there's a lot more wiggle, which means less torsional strain in cyclopentane, but still it's constrained by the fact that it's in a small ring. When you go up to cyclohexane, you notice that it's really not flat at all. And so the idea that Alfred von Baer had about the bond angles kind of falls away, because it's not planar at all, and he had assumed that they would be. And we'll talk about the actual angles in a minute. If you'll notice that it's not really flat at all, and so if we look down any two bonds that are parallel to each other, you see this one and this one are parallel. This one right here between 1 and 6 and between 3 and 4 are parallel to each other, and so on. So you can look at two at a time. And so if we look at these two, and they didn't draw these out in more detail just to keep it a little easier to see, but you have perfect 60-degree dihedral angles around this bond and also around this bond. And so we want to talk a little bit more about cyclohexane also. And the book didn't do it, but I wanted to also talk about cycloheptane because we wanted to see why the strains go back up. And again, if you pick a conformer of cycloheptane and look for the possibility for there to be some steric strain, you can see there's a lot of eclipsing going on, or near eclipsing going on, as you look around this molecule. And you can try some other conformers and you'll see that you have a mixture of some good dihedral angles and some eclipse dihedral angles close to zero. And so even though you will have gotten away at this point from any problems with angle strain because of it not being flat, there's pretty much no torsional strain because it's gotten where it's pretty floppy, but you've increased again the amount of steric strain due to this dihedral angle problem. And so let's talk about those angles for a minute. It takes 3 points to make a plane, which is a triangle, and if you have an equilateral triangle, then the angles in an equilateral triangle would be 60 degrees. So if you assume that cyclopropane is an equilateral triangle, which it is, then it would have angle strain of 49, a difference of 49 from the ideal of 109.5. And that is the maximum amount of torsional, of angle strain in all of these examples. It is also the maximum amount of torsional strain because 3 points make a plane. It can't wiggle at all, and everybody's eclipsing each other exactly, and so all the kinds of strains that we're talking about are maxed out in cyclopropane. Now, in case you're wondering, well, gee, can such a thing even really exist? The answer is yes. There are naturally occurring cyclopropane rings in things like chrysanthemum flowers, in pyrethrins, which we use for ant poison now. So even though they're strained, they do exist. Now, if you go to a square, the geometric square, the angles are 90 degrees. That's a difference of 19 from the ideal 109.5. And so it's still got, a lot of angle strain. It's got a fair amount of torsional strain because it can't rotate the bonds much at all. And there's a lot of near eclipsing or total eclipsing going on, so the steric strain is also still pretty high. Pentagon was the one that von Baer thought was going to be the most stable, and the reason was because the angles in a regular pentagon are 108 degrees, which is really close, a difference of about 1 to close to the 109.5 for an sp3 carbon. So that, he said, that would be the most stable ring. There's still some torsional strain because it can wiggle, but not a super amount. And steric strain, there's still a little bit of that. When you get to the hexagon, if it were flat, a flat hexagon would have angles of 120 degrees, which would be 11 different from the 109.5. But it wouldn't have, it doesn't have any torsional strain really, other than the fact that there's these carbons are pinned into a ring, but they still have a lot of freedom of motion. And beyond this point, there's really no more real torsional strain in any of these rings. As you get larger and larger, they start really acting more and more like open chains. With respect to torsional strain, it's gone. And the steric strain, we saw from the pictures, there was not any steric strain in the chair form of cyclohexane, and yet some came back when we looked at cycloheptane, which is compared to a regular heptagon would have had a lot of angle strain, but again, because it's not flat, it doesn't really. And this torsional strain, like I said, is really gone. So this column right here for angle strain is what it would have been if the molecule had been flat. And really the only one in this whole series that is really flat is the cyclopropane. So here was our chart of what it really looks like. And so we've got the most strains of all the strains are in cyclopropane. Still quite a lot in cyclobutane, and then it drops off a lot when you go to the 5s and 6s is 0 for everything, and then these go back up because of steric strain, and there's not really a problem with angle strain or torsional strain after this. And then when you get out here, none of it matters anymore. So that's how we can explain the experimental results for these rings. Now let's talk a little bit more about cyclopropane. I said it's actually a little more reactive than the other cycloalkanes, and when you say something's more reactive, what you really mean is that there's probably some weaker bonds in there that are easier to break. And the angle strain is a big part of the problem because the bonds really can't overlap as efficiently as they would like. Remember that an ideal sigma bond would have the electronic distribution evenly distributed about this imaginary line which connects these two atoms, and it would be created by a head-to-head overlap of orbitals, and that's how you would get this typical bond angle of about 109.5. Well, in cyclopropane, the orbitals can't quite overlap head-to-head. They're a little bit of an angle, and so this bond is bent a little bit, and so we call it a banana bond. And we say it has some pi character because remember the extreme case of side-to-side overlap would be what you get when you have two p orbitals overlap to make a pi bond. So this isn't quite head-to-head. It's not quite side-to-side. It's somewhere in between, but it's obviously not as good as ideal sigma bond would be, and so these guys are a little bit more reactive. You won't see any examples of that increased reactivity in this book, however. Alright, and we also want to talk a little bit more about cyclohexane. Cyclohexane is the most stable ring until you get to the really large ones, and it's been studied quite a bit, and we'll learn more about why that is as we go along. One of the shapes that we've got here, it looks kind of like, if you look at the drawing here, it looks kind of like a chair. We call it a chair form. I think of it more like a chaise lounge, but anyway, it's a chair is what it's called. And here was our end view of it, and you'll notice that this is a conformation, and if we wiggle this a little bit, we could get into some other conformations, and this one is called a boat. And this boat has some strains in it that you don't find if it's in the chair conformation. In other words, these guys right here actually can interact with each other sterically. It doesn't look like it so much in this drawing, but if you build some models, especially if you had some space filling models, you'd see it a little bit better. And that's called a boat, and this one is a twist boat, so it's kind of halfway between one chair and the next, and it goes kind of through these things to get to the other chair. And so this one's called a twist boat, and if you really look at it, you can tell there's some eclipsing going on. So it doesn't really like to stay in these conformers. It wants to be in a chair. There are some molecules that have the rings tied into a boat conformation, but just left to its own devices, a plain old cyclohexane ring will stay in a chair. So let's talk some more about that chair. These carbons each have two hydrogens on them. So in this drawing, there are three hydrogens that are pointing straight up or straight down, perpendicular to the quote-unquote plane of the carbon. So if you imagine that you look at this view, if you actually captured all these carbons and some of the hydrogens kind of in a plane, a plane has no thickness, so it's more like Texas toast, okay? So if you captured all of these atoms in here, then coming out perpendicular to that plane, you'd have some hydrogens, and so these are these here, perpendicular to the plane of the atoms, up or down, and they alternate up, down, going around the ring. By the same token, if you were to catch all these atoms in the plane of the ring, you'd catch some of the hydrogens. Okay, so these are the ones that are colored in here in blue, and those are called the equatorial hydrogens. And also those alternate up and down around the ring. And you'll notice what they did here is they highlighted and colored their parallel to some of the ring carbon-carbon bonds. Okay? And so as you look at the whole picture, the axial hydrogens are perpendicular up, the next carbon over the axial hydrogen is down, and the equatorial on the same carbon is up. Now it's not straight up, so I would say up-ish, down-ish, up-ish, down-ish, and they alternate around the ring. And so if you look at this ball and stick picture, you get another idea of why we call them equatorial, because you kind of caught them all as you sort of grab that molecule. And equatorial is more stable than axial once we start looking at groups on this ring. So let's say we replace one of those hydrogens with a halogen like bromine. So it's this big red ball on here. Now it doesn't look too bad, but you've got to remember that it actually takes up some space. And so we're interested in what is the difference in the spatial requirement for this guy if it's in an axial position versus an equatorial position. In other words, how much energy difference is there if this ring flips from one to the other? And you'll notice that if it's in this conformation and we flip it to this conformation, everybody who was axial flips to equatorial and vice versa, and it's easy to see once you put, some marker on there like that. Alright, so here's the same idea, and this time we have a methyl group. And what we want to see is why is it that the axial position is not as stable as the equatorial position, and it's because when it's in this axial position, you can actually get some crowding by the hydrogens, which are 3 atoms away because they are also axial. So if you count 1, 2, 3 on the third carbon away, there's a hydrogen in an axial position. The methyl is in an axial position, so there's some crowding, then that's a steric problem. Or 1, 2, 3 away, there's another one. Okay, so here's the skeletal drawing of that. So there's a 1, 3, and the numbers don't have anything to do with numbering it for the purposes of nomenclature. We're just talking about 3 atoms apart. Okay, so our reference point is, this is carbon number 1, so 3 atoms in either direction, we get another axial hydrogen. And those things crowd, whereas if this guy flips to where the methyl is equatorial, now it's out here, it's out of the way. And these are some space-filling models where they've put red blobs for the axial hydrogens and blue blobs for the equatorial hydrogens. And you can see how these guys are kind of close together right here, but out here there's nothing really nearby when this guy is equatorial. And they've used the uneven equilibrium arrows to show that it's mostly in the equatorial position. So we can use this information to figure out how much space do things take up. And so this is a table that's in your book of how much energy it takes to cause a ring with various groups on it. We're going to just label these groups Y, okay? With all these different groups on it, how much energy does it take to flip this ring? And so this table is for one 1,3-dioxyl interaction. Remember that there actually are 2 hydrogens that it could be interacting with at the same time. So if you're talking about a cyclohexane with just one group on it, there's actually twice this much energy is required for it to be in an axial position. And you'll see fluorine is pretty small. When you start adding larger halogens or more atoms, it goes up. It's a little out of line with C6H5. It's smaller, even though it's more atoms, and so we're kind of interested in that. And then this guy is really small. Now, what I want to say firstly is by kind of having a feel for this series, it gives you an idea about how much space groups take. So anytime you're not sure about what's bigger, you can flip back and find this table, and you'll have an idea about what's bigger than what. In other words, a chlorine doesn't have as much spatial requirement as a methyl group. And so here's a question, why does this group, which has 2 atoms, need less space than a fluorine, which is only 1 atom? And if you think about it, you might be able to figure this out. There's a triple bond between the carbon and the nitrogen, so what hybridization is that? Well, the carbon must be sp, and the bond angles for sp are 180 degrees. What that means is that the carbon and the nitrogen are sticking up perpendicular to this plane, and so it's really hard for there to be any interaction because they're just going straight up and out of the way. Which one of these groups is the largest? Well, it's going to be the one with the biggest number. Okay, so this is a T-butyl group, and so the actual number for 2 hydrogen to T-butyl group interactions would be 22.8. So one question you might have is, well, can the chair flip at room temperature? And the answer is pretty much, but when you get to a number that large, it pretty much wants to stop flipping at that point. And so we can take advantage of that to study some things, which we will do later on. The implications of being able to freeze the ring will enable us to understand some things mechanistically in a later chapter. Now this is just a little table that kind of summarizes, if you have 2 things on the ring, then they're either going to be axial or equatorial. And so it depends on whether they're cis to each other or trans to each other, and how they are with respect to each other. And you don't have to memorize this table, but you can kind of get the idea that if you have things on adjacent carbons and they're cis, because axial and equatorial both alternate up and down around the ring, if you looked at one of them being axial and you wanted to have cis, the one on the next carbon over to be on the same side would have to be equatorial. So that's all this table is telling you, is how that works. And whichever group is larger wants to be equatorial because that's more stable. It's less crowded by that 1,3 diaxial problem. So let's see how we use that. So we're going to practice by drawing the most stable chair conformer of trans 1-bromo-3-T-butyl cyclohexane. So before you do anything else, what you need to be able to do is to draw yourself a flat picture, so you know what things you're trying to put on the ring. And I'm going to add in the geometric information that I can to show that it's trans. So I'm using the fat, bold triangle and the dashed line to show that this is up and this is down, so that's trans, and their placement on the ring with respect to each other. And then the next thing I want to know is which group is larger, because whichever group is larger, I'm going to want to put that one into an equatorial position because it's asking me to draw the most stable chair. So the most stable chair is going to have the largest group in an equatorial position. So the T-butyl group is larger, so I'm going to start by putting that one into an equatorial position. And since I want trans, I'm going to have to look to the 3rd carbon away from that, and then I'll look at that and see which way do I need to put the other guy to be trans. So here's an equatorial T-butyl group, so I've got it down. So that means that for this molecule to be trans, 1, 2, 3 carbons away, I need the bromine to be up, and that's going to be axial in this case. So there you go. So that's the right answer to this particular question. Let's try that again. This time we want to draw the least stable chair conformer of trans 1,2-diethyl cyclohexane. So we'll start again with a flat picture. So here they are, and again I've used the bold triangle and the dashed line to show you that one is up and one is down for trans, and they're on adjacent carbons. And since they're both the same thing and I want least stable, I need to put one of them into an axial position. So we'll start out drawing that, and then we'll have to decide then, okay, will the other one be axial or equatorial in order to achieve trans? And so if one of them's axial, for a 1-2 to be trans, the other one has to be axial, because remember they alternate up and down around the ring. So we knew that the first one was axial because that's the least stable, and that's what we were asked to draw. Okay, so this is something we could put, and if we draw it in and show it, this bond kind of rotating, these guys could swing around, and so this guy is interacting with both of these two hydrogens. At the same time, this one is interacting with the ones underneath here, 1,3 diaxial interactions here and here. That kind of gives you the idea that this is definitely the least stable conformer. In contrast, if you look at this drawing, this is a two-dimensional drawing again, but it is showing you the the trans. These are both equatorial. Alright, now it may not look like it in this drawing, but this is actually more stable. And it's kind of one of the bad things about limiting yourself to pictures instead of looking at some models, because it's real hard to get the idea that this is more stable than this when you don't actually look at the models. But this one really is more stable because you don't have any crowding with anything else out here. Admittedly, they're kind of in each other's way, but you can't really do anything about that. And they can swing around and get out of the way easier than they can here, because if they swing anywhere onto this side, they're going to be in somebody's way. And here they can actually swing around quite a bit without ever getting in each other's way. Some other things that we're interested in this chapter are other kinds of cyclic molecules that have more than one ring, and the general term for more than one and sort of an indeterminate number greater than one is poly, which means many, cyclic. Now in this case that's shown here, they're just two rings, and these two rings share a bond, and so we call these fused cycloalkanes. And this first one has a total of 10 carbons, and so that's where the name decalin comes from. And it's cis because the ring juncture between the two rings is cis. Both hydrogens are up. Now if you remember a 1-2 substitution pattern where they are cis, one will be axial and the other one will be equatorial. And looking at it in the chair form, you can't tell this very easily from this picture, but this chair can flip, and that will cause this chair to flip. And it's kind of got a cup shape to it, and even if it flips, it'll still have a kind of a cup shape to it. So that cis-decalin is fairly flexible from that standpoint. Whereas if you go to trans-decalin, and this shows you the trans bridgehead in the flat drawing or in the chair drawing, they're both axial. These rings can't flip. And again, you might have to build a model to see why that is, but you can't flip those rings. And cholesterol and steroids have multiple rings hooked together with trans ring junctures, and so they're fairly flat. And that's why cholesterol can build up along the walls of your arteries and things like that, because the molecules are fairly flat. They can kind of pile up on top of each other better than these kind of fluffier ones. Another way that you can have polycyclic molecules is, instead of sharing a bond, share a single atom. So this carbon right here is a member of this 5-membered ring, and this 5-membered ring, and also this 6-membered ring. So so is this carbon. It's a member of 3 different rings also. So these are called bicyclic molecules. And in case you're wondering, these things are found in nature. And here's an example. This is camphor. And camphor has a nice smell, and sometimes is used to help clear your sinuses if you have a lot of head congestion. So what is your job? In this chapter, you needed to know about nomenclature. specifically for cycloalkanes, and we also included the cis and trans geometric isomers of rings. And we do need to know how to draw or how to recognize the geometry in these rings, including the chair conformers of cyclohexanes. And we should, again, know about the three different kinds of strains: angle strain, torsional strain, and steric strain, and what that has to do with ring stability. And then, again, go over that table of the relative spatial demands of the groups, so you'll know which groups need the most space. So if you were doing a problem like we did with the most or least stable, you know what goes into an equatorial position is going to be the larger group. You know which to put there and how to draw that sort of thing. And that's the end of this chapter.